It's only maybe a tenth or maybe even hundreds of degrees. But as soon as that modulates as function of music, you will definitely hear it, because the ear is very, very sensitive.
With phase. We're hunter-gatherers.
My name is Guido Tent. I'm from Grimm Audio, one of the founders.
Okay.
We are based in the Netherlands, in Eindhoven area.
So you guys launched new monoblocks.
We did.
Which I read about. Tell me about the design. Tell me about how they came into being, what the design process looked like from beginning until now, and what you're proud of.
Yes. Well, let's start at the very beginning. One of the so-called red lines in our company is like, we never do what others do, but we always question ourselves, like, what do we want to achieve? And we start bottom up. And that doesn't mean that we invent everything ourselves, but we just look around what has been done, what has been published. And in my early Philips days, end of 90s, I met a Philips colleague, Henk, who was into audio as well, and we became good friends. And Henk already had very explicit ideas on how to make linear power amplifiers.
Mm-hmm.
And he did some prototypes by then, and they were already very good. And he addressed some distortion principles that were, I'd say, overlooked at in the majority of power amplifiers.
Like what?
Both. There's two. It's phase modulation distortion, and it's thermal distortion.
Okay.
I'll get back to that, because those are the differentiators of this amplifier. Unfortunately, Henk passed away about 10 years ago, but we saved much of his ideas in personal communications and of some written down. We actually applied some of that knowledge already in the back end of our MU2 streamer, which has also volume control.
In the analog output
stage. In the analog, exactly.
Yeah.
But we didn't make a lot of fuss about that. All those ideas piled up, and 3 years ago, when we introduced the MU2 streamer in Munich, we needed some amplifiers to go with that. And we decided to take some of the products we already had, and we brought them to Munich. They were small wooden boxes, and the setup sounded fantastic. So, of course, then you get some response like, when are you going to bring that to the market? So we took it further from there, and we have an industrial designer who actually shapes the product, and the internal works. All the design process was taken further by our development team in Eindhoven. With those two, well, with some more parameters in our focus, but let me focus on the two specific ones. The obvious ones are like enough power. This is 200 watts per channel, sufficiently damping, like 500, wide bandwidth, a wide audio bandwidth, I should say, where all parameters are constant.
Wide bandwidth up to what?
300 kilohertz, which is more than enough. Harmonic distortion is extremely low. We apply a second order feedback system with constant loop gain up to 20 kilohertz, and we have now minus 130 dB of distortion, which is actually barely visible in the noise.
Okay, so I have some questions.
Okay.
So feedback is controversial.
It is, specifically in audio.
You know, folks like Solution have their solution, which is very, very fast circuits, that there's no latency on that feedback. How do you guys reconcile feedback in a way that's positive?
Yeah, you have to apply either no feedback or a lot of feedback. Anything in between, like 20, 30 dB of loop gain, which you typically find in tube amplifiers, that's the worst spot that you can end.
Okay.
So you have to either leave it out and cope with the result of more harmonic distortions and frequency dependent behavior of output impedance and non-linearities in the output impedance, or you apply a lot. And if you want to apply a lot,
so why is applying a lot better than middle ground?
In the middle. Applying something in the middle makes it worse.
But why does playing a lot not?
Well, if you go from 0 dB feedback to 20 or 30, actually the feedback point is a mixer. And that mixer is always somewhere nonlinear.
I see.
And the result is that it generates a lot of higher harmonics. And once you apply more feedback, which means increasing the loop gain, you all start to suppress those higher harmonics as well.
Okay.
And that's the whole secret.
Got it. And you were talking earlier about thermal distortion.
Yes.
So do you fix that with some kind of biasing? Or
yes and no.
Okay.
Let me get to that. The thermal distortion, I should actually have called it dynamic thermal distortion.
Okay.
When you look at a bipolar transistor or a FET, it's the actual die, the transistor itself is very small, which means that it heats up very quickly and cools down very quickly. And that cycling is in the range of milliseconds. Unfortunately, that's in the middle of the audio band. Every parameter of the transistor, except for the color, is depending on temperature. It's in all the equations there. Wow. So you have a wandering around device trying to amplify beautiful music, which is never the same. And the effects can be suppressed by applying feedback, but you can go one step further, which means that reducing the intrinsic effect and then applying feedback takes it even further. So we do that in roughly 2 ways. One is by keeping the power dissipation in the transistor constant, which means that voltage multiplied by current is constant. And you can develop your circuit in such a way that actually happens. So you have no dynamic temperature changes in the die of the transistor. The other way is specifically in the output stage, because you can't apply that trick everywhere. In the output stage, we divide the power and the dynamics over, let me see, we divide the power over about 60 pairs of output transistors. So the power dissipation and the power dissipation change per transistor reduces significantly. And so also the distortion there, the thermal distortion is lowered.
And these are class
AB.
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 AB
Yes.
all the way, not
AB.
A.
No,
Full
AB.
AB.
AB. And the main reason for going AB, except for heat in the case of A, and full class B is not really a choice in audio design. Going AB means that you can optimize your output stage bias to flatten the output impedance. And that's, again, that's no new result that we came up with. We just applied what, I think it was Blomley in the early 70s who wrote an article about that. And he said, you have to do it like that, which is what we did.
Got it.
And then you automatically end up with a class AB design. Yes.
Great. I'm excited to listen.
Yes.
And
if you allow me, I would like to emphasize the other distortion mechanism. And then, of course, we'll have a listen. The other one is phase modulation distortion. That actually happens if you have any kind of crossover point, which is not stable as function of the amplitude of the signal. And usually when you have an amplifier design that goes up to like half or a megahertz, you wouldn't care about something changing in the megahertz or 100 kilohertz range. But with any linear system, the phase in the audio band is related to what you're doing there. And that's only maybe a tenth or maybe even hundredths of degrees. But as soon as that modulates as function of music, you will definitely hear it.
Right.
Because the ear is very, very sensitive
with phase. Totally.
Exactly.
We're hunter-gatherers.
Oh, it's so sensitive. It continues amazing as what we still hear. So what we're after is a very stable, signal-independent roll-off of the whole system. The origin is in bipolar transistors is collector emitter depletion layer, which physically actually grows or shrinks as function of the voltage.
Okay.
The higher the voltage, the lower the capacitance. And actually that's in virtually any data sheet. So that capacitance changes as function of voltage across it. And that's bad news because we want to amplify voltage. We have a changing capacitance, and the changing capacitance give a change in the roll-off point. So what we do is we try to keep the voltage across the transistor constant as much as possible, and we do that mainly by cascoding circuits. We have got some other tricks because this solution conflicts with the thermal distortion reduction solution. So there's some really clever stuff in there that I'm not gonna expose, not yet. But anyway, those two, I should say three: harmonic distortion, thermal distortion, and phase modulation distortion. Those are the focus points of the power amplifier.
Amazing. And what's the price of these monoblocks?
The price for Europe is set. We still are working on the US and Asia region. The Europe retail price, including VAT, that's 23.5K for a pair.
Okay. Wow. Very reasonable.
Yes.
Amazing.
Yeah.
I'm super excited to hear them.
Lovely. Thank you, man.
Right.
Thanks for your intriguing questions and
For sure.
having the time with me.
For sure.
My river runs to you. Blue sea, will you welcome me? My river waits reply. Oh, see, you look gracious me. I'll fetch you brew from spotted nooks. Say, see, take me. Say, see, take me.